Hey guys, we're on page 3 of the Unit 10 notes packet, and it says, do now. Now that you love derivatives so much, we shall take them away from you. Just kidding. Below you are given 6 derivatives, so we're giving you the derivative in this column, and I want you to try to figure out what the original function could have been. Why don't you pause the video, take a few minutes, and see how you do. All right, hey, welcome back. So if the derivative is 2x, I know that it came from an original that looked like this, x squared, right? When I take the derivative, I would drop the 2 down in front. However, we know that when we take a derivative, constants drop off, right? So I'm just going to put a little plus C here to show that, like, there could have been a constant over here that I don't know that dropped off when I took the derivative. So this is kind of just my insurance policy to make sure that I don't miss any constants that could have been there in that original. And then for the second one, I know that the original was 5x, because when I take the derivative of 5x, I end up with a 5. But also, there could have been a constant here, so just to be sure, let's put a plus C. And then for 3, it says we have x squared plus 2x. All right, so an x squared must have come from an original function of x cubed, right? But when I take the derivative of x cubed, I'm going to drop that 3 down in front. There's no coefficient out here, so I must have had to have an x to the third over third in order for that 3 out front to cancel when I took the derivative, okay? Then the same thing holds true for 2x. If I'm working backwards, that's going to come from the x squared, and then I'm just going to put a plus c here, just in case there was a constant that I don't know about. Let's work backwards from 1 over x squared. So 1 over x squared is the same thing as x to the negative second, right? So if I want to think about that, well, if I wanted to work backwards, right, it would have to be x to the negative second plus 1, because I'm trying to get back to the original. So it would have ended up being x to the negative first. However, there is no negative out front here, and if I drop that negative 1 down in the front, there would have had to have been a negative, right? So I'm going to divide by a negative 1 and start with a negative 1 over x, and that will have given me a derivative of this. So I'm also going to tack on the plus c. It's a little hard to see, but this is what it should have been. So for number 5, right, if I'm trying to think of the original, well, I know that the derivative of e to the x is e to the x, so that guy had to have been an e to the x. And then when I take the derivative of an x squared, I'm going to get a plain old x. But if I drop that 2 down in the front, there should be a 2 out there. So if there's no 2 out there, it means I started with a 2 out front. So I would have something like this. And then the 8 would get an x tacked on, and we would have a plus c. Then for number 6, I have 3x squared. Now, that 3x squared, that came from an x cubed. I dropped it down and reduced the power by 1. Sorry, 1. So I can just go ahead and put my original as x cubed. And then, minus 6x. So minus 6x. Well, let's think about that. If I'm working backwards, I'm going to add 1 to the to the exponent, and then I'm going to divide by the new exponent, and that's going to give me a negative 3x to start with a 2 as my exponent. Okay, and then for the 5x, I'm just going to tack an x on plus c. All right, so it kind of looked like when I was working backwards and trying to get back to the original, I kept adding 1 to the exponent, but then to get rid of any sort of coefficient out front, I would have to divide by that new exponent. So a general expression or rule for the antiderivatives of polynomials could be add 1 to the exponent, then divide by the new exponent. Question 2. Consider the antiderivatives of f of x equals x to the n, where n is a rational number. Show whether your rule gives correct antiderivatives for x to the negative fourth and x to the 1/2. Let's see. So our rule is to add 1 to the exponent, then divide by the new exponent. let's start with the first case. They give us x to the negative fourth. So if I wanted to work backwards, I would do x to the negative fourth plus 1. That would give me a negative 3, and then I would divide by the new exponent. So the original would have had to have been negative 1/3 x to the negative third, which could be written as negative 1 over 3x cubed. Let's go ahead and check and see if that would be correct by doing the following. All right, so I'm going to graph negative 1/3 x to the negative third, and then I'm going to graph its derivative and see if it's the same as the one that's on the page given. I'm going to see if this is the same as 1 over x to the fourth. Oh, it's the same. Okay, cool. So our rule did hold true. That's great. Let's try our rule for a rational exponent, x to the 1/2. So what I'm going to do is go ahead and add 1 to it. And then I'm going to divide by the new power. So when I divide by a fraction, it's the same thing as multiplication by the reciprocal. And I would have an original that looked something like this. So let's go ahead and test on our graph. Move this, scooch this over a bit. Scooch. Okay. And I'm going to graph the original that I found, or the suspected original rather. Okay, and then I'm going to graph its derivative, which is the function they gave me, right? Square root of x. Okay, now I'm going to see if the derivative of f1 of x is the same as the one that they gave me. Yay, they're the same. Okay, so my rule does hold true. So think about just how the power rule holds true for all polynomials, rational exponents, and negative exponents. The same seems to be holding true for integrating, so that's pretty cool. This is starting to feel like the power rule just moving backwards. Are there any rational values of n for which your rule does not apply, or why? Let's see. Well, if I have x to the negative first, right? I'm trying to work backwards from there. I would add 1 to the exponent, and that would give me a 0. And then I would divide by 0. You can't do that. So I would say that it does not work for x to the negative first. And that happens because what is the derivative of the ln of x? It's 1 over x. So if I'm trying to work backwards from 1 over x, it is not going to yield a polynomial. It's going to become the ln of x, okay? But we'll get to that later on. An aside, remember the following true or false question. If f prime of x equals g prime of x, then f of x equals g of x. We're going to try to answer it again here, okay? Well, we just talked about this pesky little plus c at the end of every single function that we integrate. And that plus c means that if the derivatives of two things are equal, it's not necessarily true that their originals were the same because they could have different constants that dropped off when you differentiated. Because when you integrate the original function, kind of becomes something a little different with that plus c, okay? For example, if you have something that looks like this and something that looks like this for g of x, they are not the same, yet both of their derivatives are 2x. So this counterpoint kind of proves that this is in fact false. And it's all because of the plus c. So that was a good thought exercise. Now let's get some real life notes here, okay? For the majority of operations and processes in math, we like to know how to do it in reverse. So when you add, the opposite of adding is subtracting. The opposite of multiplication is division. The opposite of an exponent is a square root. The opposite of a derivative is a integral, right? So that's kind of what we're doing here. When we have a function and we differentiate it or take the derivative, we can also work backwards and do something called integrate or find the antiderivative to get back to the original function, okay? So we will learn rules for integrating functions starting with polynomials, and this can be viewed as going from a derivative back to its original. So let's start with some formal notation. So the integral of f of x is written like this. The dx tacked on at the end here of the integral means with respect to x. And he is the differential we talked about in Riemann sums. So remember when we kept adding up all those little skinny rectangles, and then we let the number of rectangles n approach infinity? Then that became the stretched out summation symbol, right? That is what we're talking about. That's the differential, that accumulated little area that added up to become the area under the curve. So to integrate polynomials of the form ax to the n plus bx to the n minus 1. Don't let the notation freak you out. What is this telling you? This is just a general form of a polynomial, right? The powers keep descending until we end up getting to the constant k. We do the opposite of the power rule, which is to add 1 to the power, then divide by the new power. Okay? And this is in your formula booklet as this right here. Okay? Add 1 to the power, divide by the new power. So these basic differentiation rules you're already familiar with have a corresponding integration rule. Okay? So the power rule is the one that we just talked about a lot today, and that is going to be where you drop the exponent down, then reduce the power by 1. Same thing. When you integrate a polynomial, you end up, this is kind of the same thing as saying that, right? You end up adding 1 to the power and then dividing by the new power. The constant multiple rule. If you have k times the derivative of something, when you integrate, you can pull the constant out. So what it's kind of saying is, I'll give you the words for this one. So if you have, let's say you start with f of x, right? And then you take its derivative. Let's say f of x was this, right? And you take its derivative, it's going to be a 2, right? If you integrate 2 dx, you end up getting 2x plus c. Okay, so it's kind of just saying that like this 2 never goes away. When you have a constant, you can also just pull it out of the integral if you want. You would end up getting the same thing. Okay, so that's kind of the constant multiple rule. Sum or difference, you can split up integrals with pluses or minuses and split them up into 2 different integrals if that makes your life easier. And just like the derivative of a constant is 0, when you integrate a constant, you just tack on an x and a plus c. Other basic integrals that you're going to need to stuff into your brains are the integral of 1 over x. That's going to give us the absolute value of the ln of the absolute value of x plus c. And the integral of sine is going to be negative cosine. The integral of cosine is going to be sine. And then the integral of e to the x is going to be e to the x. And then they all have a plus c on the end because those constants drop off when we differentiate. Okay? Easy ways to remember these two. So you remember the song, the derivative of sine is cosine. Well, if you're taking the derivative of sine, it gets you to cosine. So if you're integrating cosine, you're going to end back up at sine. That helps you with this one. And then for the other one, if you're the derivative of cosine's negative sine, if you're differentiating this way, when you work backwards, remember how up here we said that you can pull a constant out in front? I can pull that -1 out front, and this would become the derivative of sine is cosine. So if I'm integrating and working backwards, you would have to end up back at negative cosine of x because of that negative. Okay, so that's a way to remember that one as well. And then these you can just memorize. Okay. Let's do these two little examples on the next page. So if f prime of x is equal to 6x squared plus x plus 7, let's find the original. Okay, so I'm going to integrate f prime of x dx, and that should get me back to the original. So let's do it. I'm going to integrate 6x squared plus x plus 7. Don't forget your dx, okay? So the sum or difference rule tells me that when I'm integrating a polynomial, I can work piece by piece. I can either think about it as split up like this, but that seems like a little time consuming, right? So why don't we just work piece by piece, and you'll end up getting the exact same answer if you split up all the different pieces along the pluses and minuses, okay? So if I integrated piece by piece, I would have 6x squared. I add 1 to the exponent and then divide by the new power, plus x to the first. I add 1 to the exponent and then divide by the new power, plus 7. When I have a constant, I tack on an x, plus c. Let's go ahead and reduce. So 6 divided by 3 will give me 2x cubed plus 1/2 x squared plus 7x plus c. That is my answer to example 1. Let's look at example 2. It says find the integral of 10x minus 6 square root of x dx. Again, you can use your integral rules to split this up if that kind of helps you get your head around this easier. We can even pull the 6 out front and rewrite it like this if I wanted. We could pull the 10 out front and rewrite this like this if we wanted. Sure, why not? Sky's the limit. And then I'm going to rewrite this as x to the 1/2. That helps me add stuff easier, okay? So I would now have 10 times x to the 1. I add 1 and then divide by the new power, minus 6 times x to the 1/2. I add 1 and then divide by the new power. And I'm going to tack on a plus c. So let's see how we do. 10 divided by 2 is 5x squared minus, all right, 6 over 1 divided by 3 over 2 is the same thing as 6 over 1 times 2 over 3, which is the same thing as 1, 2, 4. So now I would have 4x to the 3 over 2 plus c. If you didn't feel like breaking up the integrals like that across all the different pieces, you could have had the integral of 10x minus 6 times x to the 1/2 dx, and then just worked piece by piece. Totally okay. You would have 10x squared divided by 2 minus 6x to the 3 over 2 divided by 3 over 2, and that would end up reducing to the exact same thing that you got over here. So Sometimes it's worthwhile to split them up, sometimes it's not. It's totally up to you. What I mean by splitting up is like this would be it split up, this would be it just going right ahead with it, okay? So go ahead and try these here. It says, what's the deal with this C? Read that part. It's kind of just explaining where this plus C is coming from, why we have to keep accounting for this constant that keeps cropping up, and it's all rested in the fact that when we take the derivative of a constant, it drops off, right? So pause the video, try these problems down here, and then in a few seconds we'll meet back and you can check your work. I think the only ones that were tricky, I can do them with you, were, oh please let me just scooch it over. Does this work here? Pretty good. Pretty good.